Good afternoon, everybody. Welcome. Good to see you as always. Today we're going to learn about an important concept in computer science called virtual memory. So consider a system that uses physical addressing, right? We've always, our idea about memory so far has been that it's a contiguous array of physical bytes that we can access just by giving an offset called an address. So in a system that uses physical addressing, the CPU executes, like, say, a move instruction, which generates an effective address, the physical address. And this address is actually the offset of a byte in main memory. So, here the CPU has generated a physical address of 4, sends that address to the memory, and then the memory fetches the word from at that address and then sends it back to the CPU. Now, this is, in fact, the way that very simple microcontrollers work, but it's not the way most systems work, including your phones, your desktops, your servers. These systems instead virtualize this main memory. Now, the idea of virtualization is a very important one in computer science, and it expands a lot of it, or applies to a lot of areas of computer systems. Now, when you virtualize a resource, you present the user of that resource with some different kind of view of that resource. You present typically some kind of an abstraction or some kind of a different view of the resource. And you do it by interposing on accesses to that resource. So in all cases, there's some resource and you want to virtualize it. And you do that by intercepting or interposing on the accesses to that resource. Okay. And then we saw this when we created wrapper functions for like malloc when I was showing you interpositioning. The same technique is used to virtualize a resource. And once you've intercepted that access, then you can deal with it any way you want. And so that's how you have sort of full power to change the view of that resource. Okay. So a good example, you saw this when we looked at disks. And physically, disk consists of cylinders, tracks, sectors, platters, surfaces. And to access a particular sector on one of those disks, you have to specify the cylinder and the track and the surface. Okay. But we saw that the view that disk controllers present is actually different. It's a virtualized view of the disk. And the controller instead presents to the kernel a view of the disk as a sequence of logical blocks. Okay. And it presents that view by intercepting the requests from the kernel for I/O and changing those logical block numbers that the kernel sends into the actual physical address. Okay, so that's a very important example of virtualization in a system. Now, the memory is a crucial resource in the system, and what we found is that it's useful to virtualize that memory resource. Okay, and the way this is done, you remember before we virtualized the disk by having the disk controller intercept request. In the case of the main memory resource, the requests are actually intercepted by a piece of hardware called the MMU, the Memory Management Unit. So the way this works is that the CPU executes an instruction. Say it's a move instruction that generates some effective address. So this is actually a virtual address. The CPU sends that address to the MMU, which goes through a process called address translation, which we'll study later today. And it converts that virtual address, in this case 4100, into a physical address, 4, which actually corresponds to the address of the data object that we want. Okay, so once the MMU translates the virtual address to a physical address, then the memory will return the word at that address. So this, you might wonder, why in the world would you want to do this? Well, it turns out there's all kinds of good reasons to virtualize the address space. And so before I can explain those to you, let me just define a few terms. So an address space is a set of addresses. Okay, so an address space is a set, not of data bytes, but of the addresses of those bytes. And a linear address space is an ordered set of contiguous non-negative integers. Okay, so just 0, 1, 2, 3, 4, 5, and so on. The virtual address space is a set of n equal 2 to the n virtual addresses. It's a linear address space. And the physical address space is a set of m equal 2m physical addresses. Okay. And so typically the virtual address space is usually much larger than the physical address space. Okay, the physical address space corresponds to the amount of DRAM that you actually have in the system. The virtual address space is the same for all processes running on that system. Okay. Now, why do we want to implement virtual memory? Why do this? Why do this level of indirection with the MMU? Well, there's really three big reasons. So the first is that virtual memory uses the DRAM as a cache for the actual data stored on disk. Okay, so you can think of virtual memory as a DRAM cache for data stored on the disk. And this allows us to use the memory much more efficiently because we only need to cache items that are frequently used, right? It's just the same idea that we learned when we talked about caches and locality. So that's one thing. We can use the memory much more efficiently by only using the portions of the virtual address space, by only actually storing the portions of the virtual address space in the physical memory. Okay. The second thing is it greatly simplifies memory management. So we saw it, every process has the same view, right? There's code code and data are always loaded at the same address. The stack is at the top of the user visible address space. So, and every process has the same similar looking virtual address space, but in actuality, that the memory that corresponds to those addresses is actually scattered all over main memory. Right? Okay, so that's a really important benefit of virtual memory. And then finally, it allows us to protect accesses. So remember, we had a process. We saw that a process provides this separate address space that's protected from accesses by other processes. Okay, so virtual memory allows us to create these separate, protected, private address spaces. Okay, and so what we'll do today, we'll look in more detail at these three ideas, and then we'll go into the specifics of address translation. So I'm going to, for the first part of this lecture, we're going to talk about address translation just in kind of high-level terms. But then we'll go into the details at the end. You can see how it really works. Okay, so let's look at VM as a tool for caching. So conceptually, you can think of your virtual memory as a sequence of bytes stored on disk. Okay, and then the contents of that virtual memory stored on disk are cached in DRAM. Okay, so think of the DRAM as a cache for this array of contiguous bytes stored on the disk. And just like any cache, the data is broken up into blocks. Okay, and then we have so here we have and those blocks for virtual memory systems are called pages. They're typically much larger than the cache blocks that we studied. So 4K bytes typically instead of the 64 bytes like that we learned about when we studied cache memories. So this virtual memory, conceptually, you can think of it as being a sequence of pages stored on the disk, so-called virtual pages. And each of these pages we'll identify with a number. So here's virtual page 0, virtual page 1. And then a subset of those pages are stored in the physical memory, in the physical DRAM memory. And then there's some mapping function that tells us which pages have been cached. Okay, so in this case, I've just shown a snapshot where we have 3 virtual pages cached somewhere in DRAM. Okay, and there's no relation between the virtual page number and the physical page number that it's mapped to. Some of these pages are not cached, so they're still stored on disk. So in this case, VP2 is still stored on disk. And there's some pages which aren't even allocated, so they don't exist on the disk yet. Is a way to think of that, right? Because we really wouldn't want to store every single page in an address space that's size 2 to the 48th. We really wouldn't want to store all those on disk. So most of the address space is unallocated. Okay. So we can just think of this. So this DRAM is just a cache, but it has a much different organization than the cache memories we studied earlier. And the difference is driven by the enormous miss penalty when you go from, if you have a cache in DRAM, the miss penalty to fetch a data item from the disk is huge. Right? So the design of this virtual memory cache is totally driven by this enormous miss penalty. And so as a result, the blocks are larger. So remember, we talked about that the block size is kind of a trade-off between sort of being able to usefully amortize the cost of fetching that block versus sort of consuming too much of this scarce cache space. Right? So in this case, our cache memories were 64-byte blocks. Most virtual memory systems have like 4K byte blocks with an option to increase to 4 megabytes in the case of x86. And now this cache, another consequence of the enormous miss penalty is that you really want to have as large associativity as you can. You remember we saw with direct map caches that were subject to these conflict misses. And if you increase the associativity of the cache, you reduce the probability of those conflict misses, but you never completely eliminate them until you have a fully associative cache with just one set. Okay, so in a virtual memory cache, it's fully associative. There's one set, and each virtual page can go anywhere in the cache. Okay. So this requires a really complicated mapping function. Somehow we're going to have to keep track of where all these cached pages are. Right? And we can't really do a search. That would be way too inexpensive. So you remember with a cache memory, the hardware actually did a search within the set, a parallel search to try to find a cache line. But with a software cache like this, that's not feasible. Right, so somehow we're going to have to remember where these cached blocks are in this very large set. And again, because it's so expensive, if you make a mistake, when you're trying to identify a victim page, if you make a mistake and you evict a page that then is referenced again in the near future, you pay a big price for it. Okay? So virtual memory caches have much more sophisticated replacement algorithms than like simple LRU that we saw with cache memories. Now, these replacement algorithms are outside of the scope of this course. You'll learn about them when you take OS. But because it's in software, we can afford to do very expensive replacement algorithms, and we can take a relatively long time to execute the code for those algorithms, because any time we spend figuring out a victim block will be much less than the cost of making a mistake and paying the access time, the miss penalty to disk. And then also as a result, virtual memory systems never use write-through, just because it takes too long. Right? So they always use write-back, and they try to defer writing anything back to the disk as long as possible. All right, now how do we keep track? Somehow we have to keep track of this complicated cache in DRAM. And the data structure that keeps track of the location of the virtual pages in memory is called the page table. Now, a page table is just a data structure in memory that the kernel maintains as part of each process context. Okay, so every process has its own page table. And it's just it's an array of so-called page table entries, or PTEs, where PTE K contains the physical address of physical page K in DRAM. Okay. So here's how it works. There's this page table in DRAM. There's virtual pages stored on disk. And then there's virtual pages stored in various physical pages in DRAM. And then the page table keeps track of where those are stored. So here we have a case. This PTE1 corresponds to virtual page 1. And in this case, it says that virtual page 1 is mapped into physical page 0. Virtual page 2 is mapped into physical page 1, and so on. Okay. Now, some of these, the pages that aren't in memory are stored on disk, the allocated pages. And so for those pages, the page table entry contains a pointer to the location of that page on disk. So think of it as a logical block number where that page can be found on the disk. And then some of the pages are not allocated, so there's a null entry in the page table. Now a page hit, so this is just a cache, right? So we have hits and misses. So a page hit occurs when there's a reference to a word in the virtual address space that's contained in a page that's cached in the DRAM. Okay. So let's say that we have, the CPU executes this move instruction. It generates a virtual address. The MMU looks up in the page table, and let's say this virtual address is somewhere within virtual page 2. Okay, so the MMU looks up the page table entry, number 2, and it extracts the physical address of that virtual page 2. Okay, so that's a hit. So in this case, the page is in memory. It's cached in memory, and so we have a hit, and now the memory can return that physical address to the MMU. Okay. Now, a miss is a reference to a word that's not cached in physical memory. So in this case, virtual page 0, 1, 2, 3 is not cached in DRAM. It's stored on the disk. So now that triggers an exception, okay, a page fault exception in the hardware. The hardware triggers the exception, and that causes a transfer of control to a chunk of code in the kernel called the page fault handler, which then selects a victim to be evicted, in this case, virtual page 4. And it fetches virtual page 3 from the disk, loads it up into memory, and then changes and then updates this page table entry to reflect the fact that virtual page 4 is now stored on disk. And if virtual page 4 had been modified at any time, it would have to write the contents of that to disk as well. So once the handler has copied virtual page 3 into memory, the instruction that caused the page fault now can be re-executed. Okay, so when the page fault handler in the kernel returns, it returns to the faulting instruction, which then re-executes. And now that page is, when the MMU checks that the PTE corresponding to that page, it finds that it's indeed cached. So now the instruction can continue, and we can fetch that whatever word at that virtual address from the DRAM. Okay, now we can allocate a new page of memory. So in this example, virtual page 0, 1, 2, 3, 4, 5 is not allocated. So if you need to, let's say you do malloc of a very large chunk of virtual address space, if those pages, if one of those pages hasn't been allocated yet, then the kernel actually, or the malloc function actually has to allocate that memory by calling a function called sbreak. Okay, and then what sbreak does is actually allocates this page and records where it's loaded. Now it would probably actually put it up into no, I guess it wouldn't actually show up in the DRAM cache until that page was touched. Okay, so just allocating space just changes this page table entry, and then when that page is actually touched, then it'll be brought into the cache. So I don't know about you, but the first time I learned about this, I was pretty appalled. It just seemed like the most inefficient, terrible idea. Right? How in the world can you afford to, on every single instruction that uses memory, do all this copying back and forth and looking up in tables? And it just seems like an awful idea. But once again, locality saves us. Okay? And it actually works because programs have locality. Okay? And it's actually fairly efficient. And the reason is that at any point of time, programs tend to access a set of pages called the working set. Okay, just by locality, right? By temporal locality, by the principle of temporal locality and spatial locality, you tend to sort of reuse the same things, reuse nearby things. Okay, and so if that working set is less than the main memory size, then all of the pages in the current working set will fit in memory, and then things will be great. Okay. But if the sum of the working set sizes for every process, right, our system's running multiple processes, if it exceeds the main memory size, then you have this meltdown where processes are thrashing each other and causing pages to be copied back and forth. So you no process ever gets its working set fully into memory. Okay, and we'll look at a technique when we look at address translation. We'll look at a little hardware cache called a translation look-aside buffer that further exploits the locality property of programs. Okay, so that's virtual memory as a tool for caching. It's also a tool for memory management, and it greatly simplifies all kinds of aspects of memory management for the kernel. So the key idea is that each process has its own virtual address space. The kernel implements this by giving each process its own separate page table in the context of that process. So it's just a data structure in the kernel that the kernel keeps for that process. And the page table for each process maps the virtual address space for that process. Now, what's interesting, so you have these pages, contiguous pages in the virtual address space, can be mapped anywhere in the DRAM, in the physical address space. So, and they can be scattered all over the place. And different virtual pages in different processes can be mapped to different physical pages. So here we have virtual page 1, which is mapped to physical page 2 in process 1. But in process 2, virtual page 1 is mapped to physical page 8. OK, so in this way, we can present a view to the programmer and to the tools that each process has a very similar address space, virtual address space, same size address space, code and data start at the same place. But then the actual pages that that process used can be scattered in memory. Okay. And then it gives us the most efficient way to use the memory. Right? If we didn't have this mechanism, think about how would you keep track? Let's say you had 50 processes running on the machine at any point in time. How in the world would you keep track of where all of the data those processes were using? Well, one technique that you could imagine, in fact, it was used in the bad old days before virtual memory. One thing you could imagine is that just give every process its own chunk of the physical address space. Just take your physical address space, partition it, and then each process gets loads and runs in its own part of the address space. Well, this has all kinds of problems, right? I mean, you could, what do you do if you add a process? So you really can't partition the address space. You really have to sort of say, well, each process gets some little chunk, and I'm going to reserve some of the address space in case there's new processes that need memory. Another problem is that now you have to write your programs. You can't just link your program ahead of time because it has to be relocated when it's loaded, right? Because you don't, a process, you don't know where in the memory it's going to go. It's going to get some chunk. So you have to either relocate all the references, the references to global symbols when it's actually loaded, or you have to create a system where all of the instructions are relative. So there's no absolute addresses. All addresses are relative to, say, the start of the program, something like that. So anyway, all of these things are just terribly complicated, and they're all solved beautifully by virtual memory. So each virtual page can be mapped to any physical page, so that really helps simplify things. And even at different times, the same virtual page can be stored in different physical pages at different times. Right? So if a page, for a while, it might be cached in one physical page, then it gets swapped out, and the next time it's referenced, it can get cached in a different physical page if it's no longer available. Right? So it provides sort of the most flexible scheduling freedom in the way that we manage the memory. And it also provides this really neat capability where you can map virtual pages to the same physical page. So this is a very simple, straightforward way for multiple processes to share certain code or data. Okay, and what you do is you just the page table entry in these different processes just points to the same physical page. So in this case, virtual page 2 points to physical page 6 in each of the page tables for process 1 and process 2. So this is how shared libraries are implemented. Right? So libc is the same code for every process running on the system. So libc just needs to be loaded once into physical memory, and then processes that want to access functions and data in libc just map the pages in their virtual address space to the physical pages where libc is actually loaded. Okay, so now there's only one copy of libc everywhere in the system, but every process thinks it's got its own copy. Now this virtual memory using virtual memory to help simplify memory management greatly simplifies linking and loading. Okay, for the reasons I mentioned before, linkers now can assume that every program is going to be loaded at exactly the same place. So the linker knows ahead of time where everything's going to be. Right? And then it can relocate all those references accordingly. Now, it really makes loading simple. so execve, the loader, if you want to load a program now, execve looks at the ELF binary, the executable binary. Okay, it sees how, it identifies how big the code and the data sections in that binary are. It allocates virtual memory starting at a fixed address for the code and data. Okay. It creates PTEs for them and marks each of them as invalid. Okay, so each PTE contains a valid mapping. So each PTE that's mapped to code and data contains a valid physical page number. But then it does this trick of setting the valid bit to 0. So when the MMU encounters a PTE whose valid bit is 0, it triggers a page fault. Right? It looks as though that page has not been initialized yet. So it's kind of a trick. Right? And then that triggers a page fault to the kernel. And then the kernel will then can then copy that page into physical memory. Okay, so the loading, actually programs and data aren't actually, they're not loaded, they're not just like copied into memory. It happens as a result of page faults. It happens as a result of misses. And it's deferred until a byte in that page is accessed. Okay, so this is called demand paging. Okay, but it's really just like any of the other caches we've looked at, right? You don't load a block into the cache until a word within that block is accessed. Okay. So loading's actually this is a very efficient mechanism, right? Because you may have a program that contains a huge array, a large array, but you're only accessing a portion of that array. So that entire array won't actually be allocated. The pages will only come into DRAM when a word within that page is touched. So if you're only accessing a portion of this extremely large array, only the data that you access gets loaded and used. Right? So it's a very, very smart mechanism and extremely helpful for allowing us to use this precious memory resource. Okay, so the third motivation for virtual memory is that it helps us protect portions of memory. So you recall that our processes, portions of our virtual address space are read-only, like the code section. Okay, and there are other portions of the address space that can only be executed by the kernel. Okay. So on systems like x86-64, it's a 64-bit system. So the pointers and addresses are 64 bits. But in actuality, the real virtual address space is 48 bits. Okay, so it's 2 to the 48th. And then the higher order bits after bit 48 are either all zeros or all ones. Okay, so that's sort of Intel's rule. Okay, and so the addresses where the high order bits are all ones are reserved for the kernel's code and the kernel's data. Okay, the addresses where all the bits are 0 are reserved for user code. Okay, so any address that contains all ones in those high order bits is by definition either code or data in the kernel. And so you can add bits to the PTE that specify whether certain virtual pages can be accessed by user code or if they have to be accessed by the kernel. So this is so-called supervisor mode. And you can also add bits that control whether that page can be read, written, or executed. Okay, so this execute bit is new with x86-64. It didn't exist in 32-bit x86 systems. And this is the This is the technique that's used now to try to prevent against attack lab code injection style attacks, because it makes it impossible. If this bit is set, you can't load instructions from any byte within that page. And so, in fact, it was this the introduction of this execute bit that sort of led to things like return-oriented programming attacks, like you did in your attack lab. Okay, so this by just this simple technique of adding bits to the PTE, we provide a way, an automatic way to protect different parts of our virtual address space from unauthorized accesses. And then the MMU actually checks these bits on each access. And if there's a problem, you know, if you're trying to do a write and the write bit's not enabled, then it throws an exception, which then the kernel deals with. Okay, so far I've been talking about address translation in kind of high level terms. So let's get down to details and see how it really works. Okay, so we're given a virtual address of n elements, a physical address of m elements. Like I said before, n is usually larger than m, but it doesn't have to be. Okay, it's perfectly. There's no reason m could be much larger than n, and it's typically not, but it could be. And so given these two address spaces, we have a map function that maps from V to P with an optional empty set, or an additional empty set. And so for virtual address A, map A is equal to A prime if the data at virtual address A is at physical address A prime. Okay, so I mean that's just what it's just a little more formal way to say what we've been talking about before with our diagrams. And then map A is the empty set if the data at virtual address A is not in physical memory. Okay, so just for a summary, I'm going to put up a list of all the symbols we're going to be using in address translation, but this is just for a summary. This is just for reference if you're using the slides later on. Okay, so here's how address translation with a page table works. So we're given some virtual address that consists of n bits. And we have blocks that consist of whose size can be represented with p bits. Okay. So think about this now. So this is very similar to what we looked at when we did caching, you know, the address bits for a cache. So these first p bits correspond to the page offset. So this is analogous to the blocks offsets that we saw with caches. And then the remaining bits correspond to the virtual page number. So remember, this is fully associative, right? So there's only one set. So in a fully associative cache, everything after the block offset is tag. So think of this as like a tag. This is what uniquely identifies this block. Okay. And in virtual memory parlance, we refer to it as a virtual page number. Now, the page table, the beginning of the page table is pointed to by this page table base register. On Intel systems, it's called CR3, control register 3. But this register contains the physical address of the page table in memory. Okay, the beginning of that. And so when the CPU presents a virtual address to the MMU, it takes the virtual page number and uses that as an index into the page table. Okay. And that identifies a page table entry which contains, if this is mapped into memory, it contains the physical address of the corresponding physical page. Okay? So the whole purpose of address translation is to come up, you're given a virtual address, and you want to come up with a corresponding physical address. Okay. So the physical address, the physical page number portion of the physical address comes out of the page table entry. And this is interesting. The physical page offset portion of the physical address comes out of the virtual page offset, and those bits are identical. Okay, so now you should convince yourself that this is true, right? The offset in a virtual block is going to be the same as the offset in a physical block, right? They're the same size blocks. And you can also see why this virtual page number identifies the page number in the page table. So imagine a virtual address that's all zeros. Okay, all zeros. So it's virtual address 0. And now that will have a virtual page number of 0. And the byte at that address will be at offset 0. Okay. Now increment by 1, virtual address 1. So that'll be in an offset of 1, and it'll be in the same virtual page of 0. Right? Now keep incrementing until all of the bits in the virtual page offset are 1s. And the virtual page number is 0. Okay, so this is the last byte in that virtual page 0. Now increment one more time. The 1 bit carries over to the virtual page number. So now we go to the next virtual page, and it's at an offset of 0. Okay, so can you see it's sort of obvious when you think about it like that. You know why we can just take these bits after the virtual page offset and use them to uniquely identify what virtual page we're working with. Okay, so let's see how a hit works in this system in more detail. So our CPU sends a virtual address to the MMU as a result of executing a move instruction or call or return or any kind of control transfer. The MMU looks up the PTE, so it fetches the PTE from the page table stored in memory. So this is actually going off the chip onto memory, into this PTE stored in memory. It fetches the PTE, extracts and uses that PTE to construct the physical address. Okay, and then it sends that physical address to the cache and memory system, which eventually results in the data being returned back to the CPU. Okay, so even for a hit, we still have memory references, right? Because we have to fetch that page table entry. Now, a miss is, in this parlance, is called a page fault. So in this case, the same thing happens as before. The CPU sends the virtual address to the MMU. The MMU fetches the PTE from memory. But then when the MMU looks at the PTE, it sees that there's either an invalid valid bit or a 0 valid bit, or it's indicated that the data is stored on disk. And so in that case, the MMU triggers a page fault exception, which transfers control to this page fault handler. The handler identifies a victim, and if it's been modified, copies it out to disk. Then it fetches the new page from disk into memory and up through the cache hierarchy. Okay. And then it causes that then the handler returns to the process. And when a handler for a fault returns, it causes the faulting instruction to re-execute. So now the move instruction that faulted is re-executes, but this time there's a page hit. Now you may be interested how the cache is integrated into all of this. So the MMU fetches page table entries, so it passes page table addresses to the cache. And if those miss, those go to memory. the memory returns those page table entries to the cache, and then ultimately to the MMU. The MMU constructs that physical address, and then it sends that physical address to the cache. Right? So with caching, the way we've been, caching's done using physical addresses. Okay. In this case, it's also possible to construct caches that work with virtual addresses. But yes?
How is the virtual address space implemented on disk? Is it just like whatever free space is available? Or?
Yeah, so we'll get into that. OK, so the question is, how is the virtual address space implemented on disk? And what it actually does, it does a much more efficient thing than the sort of abstract model that I described. So most pages, there's an option when you allocate a new virtual memory page. You can allocate it so that it's all zeros. Okay, so there's a special, you can say, I want to allocate a page of all zeros. In that case, that page doesn't need to ever get stored on disk. Right? It's just the memory. It's as though it was created on disk and then loaded into memory. So those pages that are all zeros don't exist on disk. When pages are modified, it's a little more, pages can be mapped to particular files. For example, when we load an ELF binary, the pages that correspond to the code are actually mapped to the bytes in the binary that contain the code. So that when you miss on that page, it brings in those code pages. Okay, so pages can be mapped to user-level files on disk, or not. They can be anonymous and not mapped. So if they're mapped to user-level files and you write to a page, then it'll get written back to the page that it's mapped to. If it's not mapped to any page, it's stored in this area called the swap area, or the swap file. Okay. Yes?
When you load a page from disk into memory, does a portion of that page get loaded from memory to cache into like the L1?
Oh yeah, so the question is, when you load a page from disk into memory, does it also get cached in the cache memory hierarchy? And the answer is yes. So if you load an entire page, that page will be broken up into blocks, 64-byte blocks, and loaded into the cache. So everything that you fetch from the cache goes through from the memory goes through the cache hierarchy. Okay, so I claim that virtual memory works because of locality. And that's true, but if we still had to fetch, if every time we had a miss, we still had to go to memory, it would be too inefficient. Okay, so the MMU speeds up this translation process by caching page table entries in a hardware cache within the MMU called the translation look-aside buffer, or TLB. So the TLB is a hardware cache that caches PTEs, page table entries. And it contains a cache of the most recently, it's just like any other cache. So it contains a cache of the most recently used page table entries. And so the MMU, remember the unique part of a virtual address that defines a virtual page is the virtual page number bits. Okay, so the TLB uses the VPN portion of the virtual address to access it. And so that just like any other set, it has a set of set index bits, which are just determined by how many entries or how many sets the TLB has. And it has a tag for the remaining bits to disambiguate any cache lines or PTEs that map to the same set. Okay, so the VPN or the TLB index maps to this particular set, and then it uses the TLB uses the TLBT bits to disambiguate and determine if the PTE that it's looking for is really stored in the cache. Okay, so the way this works is CPU generates a virtual address. It goes through the MMU. The MMU, instead of looking in memory and directly going to the page table entry, it first asks the TLB if it has that. It sends it the VPN and says, do you have this virtual page, the PTE for this virtual page? And if it does, the TLB returns a hit, and it returns that page table entry, which the MMU can then use to construct the physical address to send to the cache and memory system. Eventually, that results in the data being sent back. Now, when you have a miss, then there's this one, the MMU checks with the TLB for the PTE. It misses, so then the MMU has to go to memory, just like before. Okay, so this is, and then everything is the same. The memory returns the PTE to the MMU, which stashes it in the TLB. And just like before, if there's no room in the if a PTE has been modified, then it has to be written back out. Okay, just like any other cache. And eventually, the MMU uses that to construct a physical address, and then the data gets sent back. Okay, if you've been paying attention, unlike a couple people, if you've been paying attention, you're going to be very concerned about the size of these page tables, right? That, I mean, we've got 4K bytes. Suppose we have 4K byte pages, and our effective address space is 48 bits, like it is with an x86 64 system. Then, and we have an 8-byte page table entry. We'd need a page table of 512 gigabytes. Okay, 2 to the address space, 2 to the 48th bytes, divided by 2 to the 12th bytes per page. Okay, so that's the number of page table entries that we need. And then the size of each page table entry is 8 bytes. So we'd need almost a terabyte of DRAM just to hold the page table, right? So that obviously is not going to work. And it's obviously not how their page tables are really implemented. So the solution is to use a hierarchy of page tables. So if we have a 2-level page table, there's a first level page table called the level 1 table, which is always in memory. Okay, it's never paged out. And then there's a sequence of level 2 page tables, and they're all the same size, right? And the first level 1 table points to the beginning of the first level 2 table. So it contains a physical address that points to the base. The second level 1 table points to the second level 2 table, and so on. Okay. So if we have this kind of system, you remember most of the virtual address space is unused. Right? So if we have this kind of system, we can avoid creating many unnecessary page tables. Okay? So imagine if we have a 2-level hierarchy. So let's look at our virtual address space in this example. And what I've allocated 2K pages for code and data for this program. And then there's 6K unallocated pages. And then the stack, then there's a page that's allocated for the stack. I'm sorry, there's 1,024 pages allocated for the stack, most of which are, I'm sorry, there's a region of memory that's the size of 1,024 pages, but most of them are unallocated, and I've only allocated one for the top of the stack. Okay. So given this layout for my process, I only need 3 level 2 page tables. Okay. The first page table covers this region of my code and data, the first 1,024 pages. The next page table covers the remaining 1,024 pages. Okay, so these two level 2 page tables cover all of the code and data. Okay. And similarly, what I need for my stack, I just need one page table, and it only has one valid PTE. It's the very last one. Okay, and then I have a single level 1 table that points to the 3 level 2 tables. Okay, so with 4 page tables, I've covered the entire virtual address space. Now, the way that the MMU uses these multiple page tables to do address translation is as follows. We have the virtual page offset, which consists of the first P bits. And then the VPN, the remaining bits, the VPN, for a K-level page table are broken up into K sub-VPNs. Okay. And each is the same size. And so now in this system, the upper VPN1, which consists of the uppermost bits of the VPN, are an offset into the level 1 table, which is, as before, is pointed to by the page table base register. Okay, so VP1 is the index into the level 1 page table. Remember, the level 1 page table points to the address of the level 2, an entry, a PTE in the level 1 table, points to the address of some level 2 page table, or it contains the address of some level 2 page table. So that points to the base of this level 2 page table, and then the VPN2 bits are used as an index into that level 2 table, right, and so on. Okay. So eventually, you get at a PTE in the level K-1 table points to the beginning of the level K page table, and VPNK points to an offset within that table, which finally contains the physical address of the page that we want to access. Okay, and then that physical address is used to form the PPN portion of the physical address. And just like before, the virtual page offset is just copied directly unchanged to the physical page offset. So is that clear to everybody? Yes, question?
So does that mean that the number of levels will always be a power of 2, and there cannot be more than 6 levels?
Let's see, is it always a power of 2? Yes, at least. And it's defined by the architecture. So for Intel, it's a 4-level system. Now, why would it be, and then will it always be less than 6?
Right, because 2 to the 64. So that's
Oh, yeah, if it's a 64-bit system, yeah. Yeah, there's only, the block size is fixed, right? So that there's 12 bits here. 2 to the 12th is 4K. So the remaining, you actually have 48 bits to play with. Right? So the remaining 48 bits that's right. So if it was 4, if it was 8, it would be 6. So you're right. In this scheme, it could be at most 6. Turns out in practice, it's set at 4. And there was a question over here?
Oh, yeah, I don't understand what the point of doing this is. Like, how does this save you any space as compared to just having the one page table?
Have it like this multi-level system?
Right.
Oh, okay. So the question is,
At the end, going to have like all of the actual addresses being used, right?
yeah, the question is, how does it save you space? So the reason it saves you space is, you go back to this other figure. Maybe I didn't explain this well enough. So you see this, okay, so let's say we wanted to map this virtual address space with a single page table. We would need a PTE for every page within that address, whether it was used or not. Okay, it goes back. If we had a 48-bit address space, we'd need a page table entry for each page, virtual page in that address space. Okay, whether that page was used or not. So I mean, think about it. 2 to the 48th is several exabytes. We'd need a page table that had an entry for each virtual page in that 2 to the 48th bit address space. And most of those pages, by far, the vast majority, would never ever be used. Okay, so that's where the waste comes in. Okay, so here, with a multi-level page system, with this multi-level scheme, you only need to generate, in this case, these level 2, if it's a 2-level system, you only need to generate level 2 page tables, enough level 2 pages to cover the portion of the virtual address space that you're actually using. Okay, and that portion of the virtual address space that you're not using, like this gap right here, there's no need to have a page table. Is that clear? That's a really good, important question, but you look unconvinced.
So, would you ever have to so it says PT 2 to 7 or no, would you ever have to allocate one of those if you need to make another table?
Well, yeah, you still need a page table that has let's see, in this case, there's 4K byte pages, 4 byte PTEs, so there's 1K. You have 1K PTEs in this. So you still need a level 1 page table that has 1K PTEs. But those are only 8 bytes, right? I mean, so you still need to have space because you don't know. You're not sure which region of the address space you're going to need to cover. Okay, and it's the same thing for here. In this case, in these first 2 PTs, these first 2 level 2 page tables, their portion of the address space was actually all being used. Right? So each one of these PTEs at level 2 had to be initialized and used. Right? But in this portion of the address space that contained the stack, this third level 2 page table has most of its PTEs are null. You still have to allocate space for them, but they're null. Okay, that's a really good question. It's important. I hope that's clear. Any other questions before we go on? Sorry. Oh, okay, question.
So when you're indexing, then say you have this 64-bit address, each level of the page entry, or each level of the page tables, it just looks at part of the address, so it indexes by the first 4 bytes and then...
Exactly. Just like here, the MMU, remember, is doing all of this. This is all hardware logic. So the number of page tables levels is defined by the architecture. Okay. So the MMU takes the virtual address that's presented to it, and it uses a portion, a subset of those bits to access each page table. Okay. So it's just like, did I answer your question? Okay, so it's just like before. The level K, VPN K, is used to compute an index into the level K page table. Yes?
And then one more thing. Why are the indices arranged right to left on the diagram? Why does it start at 0 and then go n-1?
Okay, the question is, why are the indices arranged right to left? On which diagram?
So on this diagram, you have 0 at the top right.
Oh, these are the bits. This is the least significant bit. It's always bit 0. Yeah, that's a good question. So the question was, why do these, in this diagram, why are these bits labeled right to left starting at 0? And the answer is that we're indicating the bit position. So 0 is the least significant bit, and n-1 is the most significant bit. Yes, question?
So what's the overhead when we increase in the number of levels that we use
Yeah, so the question is, what's the overhead involved in these when you have these multiple levels? Now, are you talking about overhead to?
Increasing, for example, right now we use 4, how about we use 6 for the current process?
Yeah, well, so there's clearly, if you don't get TLB hits, it would be a lot of overhead because it would be, you would be fetching PTEs from multiple page tables from memory. So that, but because of locality, the chances are almost, the chances, this level 1 table covers the entire address space. So it's always going to be in the TLB. These level 2 tables are covering a huge swath of the address space. So chances are they're going to be in the TLB too, right? So as long as your program has reasonable locality, most of these lookups are going to hit in the TLB. Okay, so it turns out that the overhead with reasonably written programs is negligible. But it's a very important consideration, and you know, maybe that speaks against increasing. At some point, if you had too many page tables, you might increase the probability of misses in the TLB. So it's probably something they very carefully considered. Okay, any other questions?
Yeah.
Yeah.
So if we use segmentation plus paging, so is the address in page table the segmented linear address or real physical address?
Oh boy. The question was, how does segmentation fit into this?
Yeah.
And we're not going to go there. So in earlier Intel systems, such as actually the first Intel system I programmed was a 286. Was it the 286? No, it was the 8086. Anyway, earlier Intel systems had 16-bit addresses, which is tiny, right? It's only 2 to the 16th for your address space. And so as a hack, to try to increase the effective size of this address space, they introduced the notion of segmentation. And so there were 4-bit, there were registers, segment registers that contained 4 bits that could be applied to the address. So an address was the combination of the segment. No, it was more than. Yeah, the segment formed. The address then was a combination of the segment bits plus the address. So you could use the segment bits to create an offset. So it was effectively a 2 to the 20-bit address space. But you can only access it in 2 to the 16th chunks, right? So the segment would determine an offset into this 20-bit address space, and then from that you could address 16 bits. So it was this very unsatisfying, devilishly hard to program thing because you can only access 16-bit chunks at a time. So anyway, we're not going to. A few years later, they came to their senses and just created a real virtual memory system with linear address spaces. So. But you know, really, they're yeah, I don't know. We're just. I'm not even sure if they do address translation on those. Actually, so I'm not sure, but you really don't want to go there.
Okay. So that
Yeah.
probably doesn't exist anymore?
Oh, it does.
Okay.
It does. So the question is, it doesn't exist anymore. Everything, Intel's been incredibly good about maintaining backward compatibility. So,
Yeah.
so that stuff's all in there.
Just because we use
But there's a mode bit when you boot your system up. You set a bit that says, I want a linear address space. Okay, any other question?
So BPM1 points to
Oh no, VPN2 is the offset. Okay, so the question is, why do we care about VPN2 since it points to the level 2 table? So what gives you the beginning of the level 2 table is the PTE entry in the level 1 table. Okay, so the level 1 table points to the beginning of that level 2 table. And VPN2 gives you the offset into that level 2 table. So it finds the address by taking the base address and then VPN2 times the PTE size. So. Okay, good. Any other questions? Okay. Well, that'll do it for today. Next week, or on Thursday, we'll look at how virtual memory is implemented in real systems and in Linux.